So what we are going to do today here is that we will discuss about the 2 or 3 experiments possibly today. So theory part I will cover in today's lab session. For probably 3 experiments I will try to cover up the theory. It's parallel feeder protection, transformer differential protection, and generator differential protection. Okay. So let me start with the first. This is the experiment number 5 actually. 4 we have already completed, and part of experiment number 3 about the characteristic of directional relay that I will demonstrate in this experiment parallel feeder. Okay. So here you can see what is a parallel feeder. Parallel feeder is called as the 2 identical lines. These are the 3-phase lines connected in parallel and feeding the common load. Okay. So what is the advantage of parallel feeder? That in case if one of the line is off, still the load can be supplied by the other line. So the continuity of the supply is maintained. Okay. This is the advantage of the parallel feeder. But how different is the protection of parallel feeder from the radial feeder which we have discussed previously? That here in the case of parallel feeder, the relays at the source end are non-directional relays, whereas the relays at the load side here need to be directional relays. And the direction of the operation is away from the bus. This we have already discussed in the theory part, that if we use non-directional relay at the load side, we cannot set the relay settings. It is not practically feasible to set relay R2 and R4 if we use non-directional relay, and that is why the relay at the load end, these 2 relays required to be directional relay with operating direction from away from the bus. So for any fault on line 1, let's say any fault on line 1, these 2 relay R1 and R2 will trip because the current will be fed from this direction. Relay R4 will never operate for this fault because it is in the opposite direction, it is inoperative direction. Directional relay are the relay which operate on the phase angle between the voltage and current fed to the relay. Okay, when the value of the angle, or you can say when the current is reversed, the value of the phase angle changes more than 90, and hence the torque will be reversed. So this relay R4 will never operate for this fault current because it is into the bus which is in the opposite direction. Therefore, relay R2 and R1 will trip, and in the case if relay R2 fails to trip, relay R3 will provide backup. Okay, because R4 is not never going to give backup to R2. Both are having opposite direction. And in a similar way, when the fault current is when the fault is on the line number 2, you can see at that time the relay R3 and relay R4 will trip. Relay R2 is never going to operate for the fault on line 2 because it is in the non-operative direction for this relay R2. And then if relay R4 fails to trip, then relay R1 will give backup to R4. So this is how the backup protection are offered in the parallel feeder. Okay. One more point you need to understand that relay R2 and R4, as they are directional relays, these 2 relays are never going to operate for any fault on load side, because for fault on the load side, current will flow in this direction, and which is not operating direction for either R2 or R4. So the relays R2 and R4 are not required to coordinate with the load. They are not going to operate for any fault on the load side. So the coordination of the load is to be done with this relay R1 and R3, because the R1 and R3 will provide backup to the relays or the protection on the load side. Okay, clear? Any doubt in this? So how the relay setting is done in this case? The relay setting is done in a way that when you know what is the total load, on the feeder. And from this total load, what we are going to do, we are going to calculate the settings of R1 and R2, which are the backup relay to R2 and R4. Although they are primary relay for line 1 and R3 is primary relay for line 2, but still they will act as a backup. And from R1, we are going to calculate setting of R4, and from R3, we are going to calculate the setting of R2. Although they are identical, the settings of R1 and R3 will be similar, as well as the settings of R2 and R4 will also be similar. So in this way, the relay settings can be done. We cannot calculate setting of R2 and R4 directly from the load, as they are directional relay. They are not going to be coordinated with the load side. Okay, remember this point. Now, in the laboratory, what we are going to do in laboratory here, you can see we have a setup where we have a single phase supply. This two are directional relay. Okay, so we know that the directional relay requires two inputs. It requires current input through CT and voltage input through PT. So the directional relay input R2 and R4 will be from CT as well as PT, because we require both the input, voltage and phase. Whereas in case of non-directional relay, only current input is given. So here the input will be given from CT. So you will see that here for this two relay, we also require PT, that is a voltage input. Okay. So this is the single phase supply, 230 volt single phase supply. Okay. This is a feeder one. You can see with the help of this 20 ohm resistances, we are making it as a feeder one. Another feeder, that is a 20 ohm and 20 ohm, 40 ohm resistance. So these two are connected in parallel. Then here we have one relay, that is 50 or 51, which is a overcurrent relay. This is a non-directional relay, okay, which is shown by arrowhead on the both the sides. And this is 67 is the number for directional overcurrent relay. So these two are the directional relay. You can see here we have a PT 230 by 110 volt. So this PT is used to give voltage input to this directional relay. And there are CTs for the current input. So these are the CTs. Okay. Then here is the load, 185 ohm load, which is connected on this two feeder. This 20 ohm is the fault resistance. So when we close switch S1, you can see the fault will be created on line 1, and this 20 ohm will limit the fault current. The purpose of this rheostat is to limit the current. So this will be the fault on line 1 when we close switch S1. And in a similar way, when we close switch S2, which is used to create a fault on line, okay. So these two switches are used to create fault on either line 1 or line 2. The control circuit is very similar to the one which we have discussed previously, radial feeder protection. In radial feeder protection, whatever control circuit we have discussed is very similar to this. Only difference here is that we have four different control logic circuits for relay 1, relay 2, relay 3, and relay 4. Okay. Then just a moment. So here what we were discussing is that we have the directional as well as non-directional relay in case of parallel feeder. And the relay setting will be in a different way. Okay, then the parallel feeder, sorry, then the radial feeder. So here we will first see that how to uh, set the relays, plug setting and time multiplier setting, and then how to perform the experiment. Okay, this is the input to the relay. You can see these two relay here are non-directional relay, induction disk relay, simple, this two relay. Whereas this two relay, you can see the number is given 67. These two are the directional relay, so which have also induction disk unit as well as induction coupling. Okay, and this two relay require both the input voltage and current input. So current input, obviously this relay also require current input. So the current input is given from CT. This is relay R1. Input to relay R1, input to relay R3. You can see here this two relay directly from CT. This is relay R2 and R4, which are directional relay. So for that, we have a input from CT and as well as input from PT. You can see this is a PT. So this two relays, 67 relay, 9 and 10. You can see here the terminal number 9 and 10 are for current input, and terminal number 7 and 8 are for the voltage input to this relay. Okay. So this arrangement is for directional release, where you need both the input voltage and voltage. Now, any doubt till now? Any doubt till now? Yes. Any doubt till now? Anyone? Yes. Satin, Pratik, Dharmesh, anyone? Avesh, any doubt? Okay. So fine. Let us go for the relay settings. How to do the relay setting? So let me draw the diagram that we use for the reference. Here we have a 230-volt single phase AC supply. This is representing the line number 1 or feeder number 1. This is the another feeder, parallel feeder. Okay, 20 ohm each. And we have a 185 ohm load here. Uh, Right. Then here we have relays. R1 and R3 are non-directional relays. Relays at towards the source. And R2 and R4, which are the relay near the load, are the directional relay with operating direction away from the bus. Okay. So then, as I have already said that this relays R2 and R4 are not required to be coordinated with the load, because any fault on the load side, these two relay are never going to operate. And that is why here first we need to calculate the settings of R1 and R3 based on the load. So for that, let us find out the total load current. How to find total load current? It is very simple. Here we have a 230 volt supply. This 20 and 20, so it is 40 ohm parallel to 40 ohm, and in series with 185 ohm, you can say. This is the total resistance of line 1, total resistance of line 2 connected in parallel. So it is 20. So 185 by 20, and this is a 230 volt. So what is the total load current? Is 40 and 40 is 20 plus, sorry, 230 by this resistance. Total voltage is 230 and total resistance is 40 parallel to 40 plus 185. So this comes 230 by 205, and that is total 1.12. Okay, 1.12. Fine. Any doubt in this? And as the this is the total load 1.12 ampere here. Which is divided into two parallel paths. So here it will be 0.56 here. Both the feeder will carry half of the load. Fine, 0.56, 0.56. Any doubt in this? Any doubt in this calculation? We did. Now see, the pickup of this relay R1 and R3, that must be greater than the total load current, not of 0.56 ampere. The reason, suppose if you calculate the pickup of R1, which should be greater than 0.56, okay. So for parallel feeder, when both the lines are working, it is fine. It will not have any issue. But suppose, let's say, when we have a fault and one of the line is tripped, what will happen? The total load will be transferred on line 1, because they are connected in parallel. One of the line trips and the total load is transferred on the line 1. And in that case, if you have calculated the current, the pickup using this only half current, relay R1 will also trip, and parallel feeder will not serve the purpose. समझ में आया क्या बोल रहा हूँ? ये दोनों रिले का जो पिकअप है वो हमें हाफ करंट यानी जो शेयर करते हैं उससे नहीं फाइंड करना है. वी हैव टू कैलकुलेट इट फ्रॉम टोटल करंट, क्योंकि अगर एक फीडर पे फॉल्ट हुआ देन द टोटल लोड विल बी ट्रांसफर्ड ऑन द अदर. और अगर आपने पिकअप यहाँ से सेट किया है ये वैल्यू लेके, then when in case when there is a feeder one trips, the other feeder will also trip because your relay calculation is not correct. तो आपको यहाँ पे जब आप रिले कैलकुलेशन कर रहे हो, प्लग सेटिंग व्हेन यू आर कैलकुलेटिंग फॉर द पैरेलल फीडर, यू हैव टू कंसीडर द टोटल लोड करंट. Okay, city ratios are 2/1. Let me write city ratios are 2/1. Right? So what we can write? The pickup of R1 and R3 should be greater than this load current, 1.12 ampere. This we have to take total load current. I am again repeating, because if feeder 1 trips, the total load will be transferred on the other feeder, and if you only consider the half of the load while relay setting, that relay will also trip in this case. Okay, so this is what we have to take care. Okay, so this is how the pickup setting will be done. This is from city primary and city primary side. You can see this is 1.12 ampere. Now we want to convert it on the secondary side. So as refer to sorry, percentage on city primary side. So divide by city ratio, that is 2/1, and convert it into percentage. In percentage of city primary, you can say, because the city ratio is 2/1. So in percentage, it is greater than or equal to, what is 1.12 by 2 is 0.56, and 100%, so it is 56% for in percentage of city primary. So plug setting should be greater than this. Okay, and what is the range available? 50% to 200%. 50% to 200% in 7 equal steps. So next step available is 75%. Obviously 50, 75, 100 we know. Okay, so the next available range for us is 75%, and that is why what we will select, the plug setting of R1 and R3 is 75% selected. You should write it down, okay, because the same calculation you have to show it in the lab file, or either you write it right now, or maybe probably you can refer to videos later on, okay, for the calculation file. Now see what we have calculated. We have calculated the plug setting of R1 and R3. Now plug setting of R2 and R4 we have to calculate. So backup to R2 is provided by R3. It is like this. Backup to R2 is provided by R3 relay, and backup to R4 is provided by R1. So actually the backup, if you remember the remote backup, to calculate the setting of the backup relay, what equation we used previously? The equation is like this. Plug setting of R1 and R3, which is a backup relay, to R2 and R4 here. It should be greater than or equal to 1.3 by 1.05 into plug setting of R2 and R4. Because R1 and R3 are providing backup to R2 and R4, their settings must be greater than this 1.3 by 1.05 times. This we have seen that the pickup may vary between this 1.3 to 1.05. But in this case, as the plug setting of R1 and R3 are available from the load, we will find it in a different way. First, we have this plug setting available. And from this we can find should be less than or equal to. Now it will be different because we know the plug setting of R1 and R3. So in parallel feeder, the settings are done in this way, where first you find the settings of non-directional relay, and from that you find the settings of directional relay for pickup value. So here we can write the plug setting of R2 and R4 should be less than or equal to 1.05 by 1.3 into what is plug setting of R1 and R3 we have selected. Here it is 75% of CT primary, so it is 2 ampere. So 75% of 2 ampere is multiply with 1.05 by divide by 1.3, that will come as 1.211 in terms of CT primary, and if we calculate it in terms of percentage, so what we do, 1.211 divided by CT primary, that is 2 into 100%. So in terms of percentage, you can see of CT primary. Fine, and this comes as less than 66.5%. So it should be less than this. So what is the range available again? 50 to 200%, and less than 66 is the range available is 50%. So what we can say that the plug setting of R2 and R4 is we can select it as a 50%. Select. Okay, it should be less than 66%. So the range available is 50%. So what we can do here, we have set the plug setting of R1 and R3, which is 75% pickup value, and plug setting of R2 and R4 we have set it to 50%. Okay, any doubt till now in this calculation? How we have calculated the plug setting of relay R1 and R3 as well as R2 and R4. Any doubt? Okay. The other setting, okay, first setting that we have calculated is plug setting, which decides the pickup of the relay. Okay, it decides the pickup of the relay. Now, the next setting that we want to find out is TMS, time multiplier setting. Okay, time multiplier setting. So for TMS, what is the process? For TMS, what do we do? For TMS, we coordinate between the primary relay and backup relay, and we add a discriminating time interval of 0.25 seconds for the successive operation of primary and backup relay pair. And for that, we consider the fastest operation of the primary relay. Okay. So for primary relay, let's say the settings of R2 and R4 and R1 and R3 will be identical. Okay. So if we calculate for any one relay, suppose if I calculate for R1, same setting will be for R3. You can see here I have written. Okay. Likewise, the settings of R2 and R4 will also be identical because these two feeders are exactly identical to each other. Okay. Now, to find the TMS, first, what we have calculated? We have calculated the pickup of R1 and R3. So let me summarize it in a result table. For relays R1 and R3, the plug setting that we have calculated in percentage is 75%. Its city primary rating is 2 ampere, and therefore the pickup of R1 and R3 75% of 2 ampere is 1.5. So the pickup of R1 and R3 is this. R2 and R4 plug setting we have calculated is 50 ampere. Its primary rating is also 2 ampere, and therefore giving as a 1 ampere pickup. Okay. This table will be useful for us to in the calculation of TMS. Now for TMS, what we are going to do? So let me draw the diagram again. This is the parallel figure, 20 ohm, 20 ohm, and here we have released R1, R2, R3, R4. This is the R2 and R4, which are the directional relay with operating direction away from the bus. And R1 and R3 here, the relays towards the source are non-directional. Okay. Fine. Now, to find the EMS, what we need to do here is that first we have to calculate the time of operation of R2 and R4 for the highest fault current. And in that case, we have to add 0.25 to obtain the time of operation of for R2 it is R3 and for R4 it is R3. Although they are as they are identical, we have to calculate only for either R2 or R4, and the same settings can be used. So what will be the maximum current that can flow through R2 or R4? So for that, let's say if fault occur here at this point. So the current through this line can be in this way from R4. This will be the maximum current that will pass through R4, because for any fault current, let's say fault occur here, the current through the R4 will be lower than this, because the 20 ohm will be the part of this loop. So we will consider fault at this point. That will give us the maximum current, and here we have a fault limiting resistance, you can see, of 20 ohm. So let us consider the equivalent circuit with 20 ohm fault resistance, and let us calculate the total fault current. Okay. So here, if the fault is at this point, just a moment, fault is at this point with the 20 ohm fault resistance, you will see. So how is this circuit going to be? You can see 185 is parallel to 20 and this 40 is parallel to 40. So the equivalent circuit will be like this. Here is the 20 ohm, 40 parallel to 40, and this is 20 parallel to 125, 185. This is the fault, 230 volt. Okay. What is the equivalent of 20 ohm parallel to 185? Tell me the equivalent. 20 ohm parallel to 185 ohm. Yes. What is the equivalent of 20 ohm parallel to 185? I'm waiting for the answer, or if I don't get an answer, I'll ask randomly to anyone. Tell me the value of 20 ohm parallel to 185. Yes. Do you have calculator? Jatin, Pratik, Dharmesh, enrollment number 3, Ravi, Vatsal, Harsh, Sanjay, Jesapa, and Bhavesh. Each of you need to reply to the answer, to the question. Okay, what is the answer? Okay, Bhavesh. Jatin, Pratik, Dharmesh. Enrollment number 3. Set your username with the enrollment number and name. We have asked this many times. You should also write your name at the end of enrollment number. Ravi, Vatsal, Harsh, Sanjay, and Jesabai. Reply to this question. The equivalent resistance of 20 ohm parallel to 185. Just a moment. Here, take it as a 40 ohm. It is 40 ohm. Okay. There is a mistake in the diagram. I think here. This is actually 40 ohm. Okay. So, Bhavesh, take this as a 40 ohm. Okay. So 40 ohm parallel to 185 ohm. Yes. Okay, correct. I have not received any single answer from anyone other than Bhavesh. Jatin, Pratik, again I am repeating. Dharmesh, Fayaz, Ravi, Vatsal, Harsh, Sanjay, and Sabai. Reply. What is the answer? Okay, Fayaz, correct. Correct, Fayaz. It is 32.80. Okay, so this is 32.88. Parallel combination of this two is 32.88 ohm, and then it is added to 20 ohm because this is parallel. And so fault current for this fault will be 230 divided by 20 plus 32.88, and that comes 230 by That is, what is the answer? 230 divided by 52.88. Okay, so that is 4.35 ampere. Here you can see. Yes, got it. Okay. So then that is correct answer, Bhavesh. 4.34 or 4.349. Now, if we apply the current divider here, what will be the current to this? So this is total current is 4.35 ampere. You can see here. And what will be the current through 40 ohm that we want to find? So current through 40 ohm is 4.35 into opposite, that is 185, divided by 40 plus 185. So that current will be 4.35 into 185 divided by total 225. So that current will be 3.57 ampere, that is passing through the relay R. Okay, when the fault occurs here, the current through the relay R4 is 3.57 and the remaining current, the difference between 4.35 and 3.57 will be flowing through the load voltage. And this total current is going to be 4. Sorry, just a moment. This is, let me correct it. Let me correct it. One more point here. This we have considered it as a parallel. Okay. So 4.35 is divided into two parts. Just a moment. Here I'll make a change. This is the total 4.35, which is divided into two parallel parts. So what is the current here? 4.35 divided by 2, because it is a parallel circuit. 4.35 divided by 2 is 2.175 here. And here also 2.175. I hope you understand what I'm saying. This is the total current. Here is the equivalent of this two. So there will be correction, Bhavesh. This is 20 ohm is the parallel of 40 and 40. So the total current you can see here, it is like this, divided into two parallel paths. So this is 2.175. And here you use 2.175 instead, because this 2.175 here is divided into two parts. One is from relay R4 and one is from the load. So into 185 divided by 2. So that comes 1.78 ampere. Okay. So remember the current through the relay, this relay is 1.78 ampere, correct? Now to find TMS, what we need to do? To find TMS, we have to find out the operating time of R4, and in that we have to add 0.25 seconds, so that is the time of operation of R4. As well as same thing will happen to R2 and R3. Now see, R1 and R3 are the backup relay to R2 and R4. So we can select the minimum time of operation for R2 and R4. So what we can write? Let us select PMS of R2 and R4 as minimum 0.1. Selected. Selected. Okay. Fine. Any doubt in this? Because this R1 and R3 are the backup relays to R1 is backup relay to R4, R3 is backup relay to R2. So we can select the minimum time for this relays at the load height, that is 0.1. Now to find PMS of R1 and R3, what we are going to do? First, consider the fault current, that is 1.78 ampere. For this, we will find the TOP of R2 and R4. Both will be same. We can say 3 upon log PSM of R2 and R4. Because they have identical setting, so we are writing into TMS of R2 and R4. So what is PSM of R2 and R4? Is IF by I pickup. What is fault current? Maximum fault current is 1.78 divided by what is I pickup? You can see pickup of R2 and R4 is 1 ampere. So that is 1.78 is the PSM. And therefore here we can write .78 into TMS is 0.1. So what will be this time? 3 upon log 1.78 into 0.1. What will be the TOP of R2 and R4? Tell me. Yes. Please tell me. 3 upon log 1.78 into 0.1. That is coming out to be 1.18 seconds. 1.19 seconds. Okay. Any other answer? Any other answer? Anyone else? Okay. 1.19 seconds. Okay. So, sorry. So for this fault here, which is just near the relay, where the fault current through the relay is 1.75, this relay will operate in 1.19 seconds. So what we can do, therefore, TOP of R1 and R3, what we can do, we can add this 0.225 second as a backup relay, and that will be 1.44 seconds. For the same fault. What it means, if relay R4 does not operate for this fault, R1 will operate in that. And suppose fault is here, for example. Okay. Then if R2 does not operate, then R3 will operate after 0.25 seconds. Now from here, you can write the equation, which is 3 upon log PSM of R1 and R3 into TMS of R1 and R3. PSM of R1 and R3 we can calculate IF by I pickup. So same fault current 1.78 ampere and pickup of R1 and R3 is 1.5 ampere. Here we have noted it down. So this comes as 1.78 by 1.78 by 1.5. That is 1.186. You substitute that here. TOP of R1 and R3 is known to us. So this is known. This is known. Here you can see. Okay. And from there, you can find the TMS of R1. So what R1 and R3? So TMS of R1 and R3 that will come if you select it finally. That will also come 0.1. Okay. Fine. Any doubt? Any doubt in this calculation? Now in this experiment, what we are going to do, let me tell you. So the settings we have done. What we are going to do here is that in this experiment, first here in this diagram, let me show you. Just like as the control circuit we have discussed previously, first we will close the breaker 1, then we'll close the breaker 2. So the line 1 will be on, and as the line 1 will be on, the total current on this line will be 1.12 ampere. Okay. Then on line 1, then we'll switch on the line 2. So total current will be same, but the total current will be divided into two parts. It's a 0.56 ampere and 0.56 ampere. So that is a parallel operation. Then in this experiment, we are going to close switch S1. So fault will be on feeder 1. So this 3 relay will pick up, and initially this 2 relay will trip and open the breaker at both the ends, because fault current is fed from both the ends. Let's say here. So it is required to trip the breaker at both the ends, and this 2 relay will trip the breaker. In case if this directional relay fails, the backup will be provided by R3 and it will trip breaker over here, because this relay is never going to operate for fault on line 1. It is in the inoperative direction. Likewise, when fault is in on line 2, when I close the switch S2, the fault will be on line number 2. And in that case, this 3 relay will pick up. This is never going to operate for this fault, because fault is fed in this way. So it is not in the operating direction to this relay. And this relay at both the ends will trip the breaker here. Fine. And in case if this directional relay fails to trip here, this relay will provide the backup and will trip the breaker. This is what we have to take as a primary protection. Then what we are going to do, we are going to also see the effect of polarizing voltage on directional relay. We know that in the absence of minimum polarizing voltage, directional relay is going to fail. It is not going to trip. So what we are going to do here, we have used a phase shifting transformer in the laboratory, and with the help of this, we are going to reduce the voltage applied to the relay voltage coil. Standard voltage is 110 volt, but we will gradually reduce this voltage applied to the relay coil intentionally And we will check that at what minimum voltage the relay fails to trip. Okay, and when directional relay fails to trip, the backup protection can be also studied at the same time. That let's say if I give only 10 volt to this directional relays intentionally, then suppose this relay is not tripped, and in that case the backup relay will provide the tripping. So that will be the backup protection we can check. And third thing that we are going to check here is that using the phase shifting transformer here, intentionally, actual operating direction of the directional relay is always away from the bus. But intentionally, what we are going to do, we are going to phase shift the input given to the relay in such a way that the relay operating direction will be reversed, which is not the case in the field. Okay, in the field, actual direction of the operation is always away from the bus, but for a laboratory demonstration, to understand the effect of the phase shift on the relay, we are going to reverse the operating direction of this two relay. Instead of into the bus, sorry, instead of out of the bus, that will be operated into the bus. So what we are going to do, when we close the switch S1, instead of relay R2, relay R4 will trip, because operating direction is reversed. And same way for when the fault is on line 2, relay R2 will trip. What we want to demonstrate here is that the effect of phase angle on directional relay. How the operating direction is decided based on the phase angle between voltage and current that we can check here. Okay. So this is what we are going to do in the parallel feeder protection. Any doubt in this experiment? Any doubt in this experiment that we are going to do? Yes, anyone having any doubt? So remember this, we will do it in the next lab. I'll show the demonstration. Meanwhile, we are also going to discuss the next experiment. So the performance of both will demonstrate in the laboratory. The next experiment is to study and perform the transformer differential protection. So we know that transformer winding is protected using against the short circuit using the bias differential relay, and we have studied the operation of bias differential relay. That bias differential relay have a two settings: basic setting and bias setting. So this is the percentage bias setting you can see, where this is called as the differential current, and this is called as the average restraint current. Here. Okay, just a moment. Sorry. So when this ratio is more than the set value, then the relay will trip. And for the internal fault, we have discussed when we have discussed the relay, that for the internal fault, the differential current will be higher, because the current will only flow through the one of the city. Through the other city, the current during the internal fault will be lower. So in that case, the differential current will be higher and average restraint current will be lower, so that the percentage bias calculated by the relay will be higher, and it will be obviously higher than set value, and the relay will trip. For external fault, As the fault current is carried by both the CT, you can see same current, the differential current will be lower, average restraint current will be higher, and that is why the percentage bias will not be satisfied. And this characteristic shows the slope. If you set, let's say, percentage bias 0.1, 0.2, 0.3, or maybe any value, then the slope here will be different, or different value of the percentage bias. As we increase the percentage bias, the slope is going to increase. And this shows here for this characteristic. Suppose if I have said percentage bias equal to 0.2, for example. Okay, this is percentage bias equal to 0.2, I have said. So if the ratio of I1 minus I2 by I1 plus I2 by 2 is more than 0.2, it is in the trip region. And if it is less than this, it is in the block region. This is how the percentage bias relay works. Clear? Clear? Fine. So what we are going to do in this case, in laboratory, we have a bias differential relay, which is called as the MBCH relay, MBCH12, one of the widely used relay for the bias differential protection. Okay. So what we are going to do in this laboratory, we have a 1 kVA single phase 230 by 115 volt single phase transformer, and this transformer, on both the sides we have put CTs. Okay, and here we can create we cannot tear up the insulation of the winding, okay, to create the fault. We cannot actually do it in that way that we can damage the insulation of the winding to create the fault. So what we can do, fault is a flow of current to an undesired path. So what we are going to do, using the switches and rheostat, we are creating the here it is the load. So we are creating the parallel path which is flowing to undesired path other than the load. So this switch S1, S2, and S3 are used to create the fault. Okay, as the CT is placed on either side of the winding, you can see this is the zone of protection. This is the zone of protection. Fine. Now, any fault outside this zone is considered as the external fault. So when we close switch S3, that fault will be considered as the external fault, which is outside the zone of protection. When we close switch S2, there will be a fault on the secondary side, which is 115 volt. And when we close the switch S1, the fault will be on the primary side, that is there on 230 volt. Okay. So what is going to happen here? First, let me show you that under normal condition, when the circuit breaker is, let's say, closed here, the contactor is closed, the current will be fed to the load. That will calculate what will be normal current. Okay, which will be simply 115 volts by 185, because 185 is the load resistance. Here we have used. So normal load current here we will have is 115 by 185. Okay. Then similar way, we will calculate the fault current for external fault by closing switch S3, fault current for internal fault closing switch S2, and fault current for internal fault on primary side. And in each case, we will find out what will be the I1 minus I2, there is a differential current, and I1 plus I2 by 2. average restraint current, and each time we will find the percentage bias for internal fault as well as for the external fault. Okay, then we, for the MBCH12 relay, we have set some percentage bias, and we'll check if the percentage bias calculated for this C fault is more than set value or not. And if it is more than set value, the relay will. Okay. Now, what is the setup of MBCH12 relay? So MBCH12 relay is a static relay. Static relay means it has no moving part. It works on using the electronics devices components. So what we do, this is the T1, CT1. Okay, this is the CT1. Let me tell you the ratio of CT1. CT1 ratio is 2 by 1. CT2 ratio is 4 by 1. We have already discussed that the current on primary and secondary side will be different in case of transformer. So CT will be not identical on primary and secondary side. So CT ratio on primary side is 2 by 1. CT ratio on the secondary side is 4 by 1. So this CT1 is connected in series with 230 volt here winding. And CT2 is connected in series with 115 volt. This is it. Okay. And the current from CT1 is injected into MBCH12 relay. You can see the number, pin number. Pin number is 23 and 27. So this is the injected current I1. This is the injected current I1. From CT1. This is injected current I2 from CT2. You can see, which is on the 115 volt side. And in this relay, it will calculate based on the injected current. If this percentage bias calculated is more than set value, then relay will trip. As it is a static relay, we have to supply the auxiliary DC supply. So we have used a rectifier that is converting 230 volt into 30 volt DC for the operation of this MBCH12 relay, which is a bias differential. Okay. So, any doubt? Now, what we are going to do here, when we'll close switch S3, it will be an external fault. So the percentage bias is not just satisfied and relay will not trip. But in the event of internal fault, either on let's say secondary side or primary side, the difference will be large and the percentage bias will be more than set value. And therefore, relay will trip instantaneously. This differential relay, bias differential relay is instantaneous in operation. We have asked this in the mid-sem. Hardly few of the students have correctly answered what is instantaneous relay. No intentional time delay. No intentional time delay, which operates within one cycle. We have not, the time of operation is within one cycle. Okay, that is what is the meaning of instantaneous operation. Okay. So here what we are going to do first, we are going to calculate the current and percentage bias for external fault and internal fault. And this is the control circuit. It is very similar way. When we'll close the press the start push button, it will energize the contactor coil. So this contactor will close, circuit will be on, and hold on will be provided by this contactor contact. The semaphore will change its position from 90 degree to 180 degree when the press button push button is pressed, start push button. When the fault will occur, MBCH to a relay 12 will operate for the internal fault. So its normally open contact will be closed, and that will energize the auxiliary relay. So auxiliary relay will give hold on to MBCH 12 contact, and this normally closed contact of auxiliary relay will be open. So the supply to the contactor coil will be disconnected, and as the supply is disconnected, the contact here will become open. So it is disconnected from the supply. Okay, this is how the works. Now if we see the calculation, so it is 230 volt single phase supply here. Transformer is 230 by 115, so secondary side is 115 volt here, and which is connected with a 185 ohm load. So normal load current you can see here is 115 by 185. So what is this? How much is the current? One 115 by 185. Yes. 0.62 ampere. This current. This is a 4 by 1 CT. This is a 2 by 1 CT. So what is the secondary current? Here is 0.62 by 4. That comes 0.155 ampere. So this current that is injected to relay coil under normal condition is 0.155. Now it is a transformer 230 by 115. So if the current here is 0.62 on 115 volt, so current on this side, primary side, if we take the CT ratio, it is 0.62. Here the voltage is half, so current is double, so it is 115 by 230. So the current here will be 0.31 ampere. You can see this current. And what will be the current on the secondary side? That is divided by CT ratio. That is again 0.155. So under normal condition, current from both the CT that is fed to relay coil, here you can see this both the current are theoretically they are identical, 0.115 ampere. So what is the differential current? Is normal condition is 0. This is I am saying ideally theoretically. However, under normal condition due to CT errors, this current will not be 0 and some small differential current will pass through the relay coil, which is called as the spill current. Okay, that I will show in the experiment. Now, when we close the switch S3 external fault, so switch S3 is closed, so circuit will be like this. This is closed. Here are our CTs. CT is 2 by 1. This CT is 4 by 1. This is 230 volt. This is 115 volt. And when the switch S3 is closed, let's say it is here. So the fault occurs outside the zone of protection and 20 ohm. This is 185 ohm. So what will be the current? 20 ohm parallel to 185 ohm. That is 18 ohm, and 115 is the volt. So volt current on the secondary side of transformer is 115 divided by 80. That comes how much? This current simply, or what you can do, it is in parallel. So you can simply add both the 115 by 20 and 115 by 185. Both are in parallel, so voltage remains same. That is also other way. So the total current here will be 6.38 ampere. This is total current is 6.38 ampere. Okay, and current through 20 ohm will be 115 by 20 ohm. So it is 115 by 20 is 5.735 ampere. And current through this 185 ohm is 115 by 185. So that is 0.62 ampere. Okay. Now what will be the current on the secondary side of CT2? So it is total current is will flow through the CT is 6.38 divided by 4. So that current will be, you can say, 6.38 divided by 4. 6.38 divided by 4. So that is 1.595 ampere. So this CT will reflect here. This current is 1.595 and CT1. So here this current on this side is 6.38 into transformation ratio is 115 by 230. So 6.38 divided by 2, 3.19, and therefore I1, small I1 on the secondary side of the CT1 is 3.19 divided by 2, that comes 1.595 ampere. So even though there is a external fault, current through this primary will remain the same, and that is why the secondary current you can see will be the same. This is theoretically, again I am saying, because of the error in the CT, you will see in the experiment that this current will not be the same. So there is a spill current flowing through the relay coil even when there is a external fault. But as if we calculate the percentage bias, still it will be 0, because I1 minus I2 upon I1 plus I2 by 2 will be still 0. So third, when we close switch S2, when we close the switch S2, because if we, let me write the percentage bias here, theoretically, percentage bias is I1 minus I2 upon I1 plus I2 by 2. So it is 0 by 1.595. I1 plus I2 is same, so it is 0. Here in this case also the percentage bias seen by the relay is 0, because differential current is 0. But when we close switch S2, you can see here, the diagram will be like this. Which will be the indication of internal fault. Here we have CT1 over here, 2 by 1. CT2 is now here, 4 by 1. You can see if switch S2 is closed, it is before the CT. Okay, this is 20 ohm, 185 ohm, 115 volt. is 230 volts. So we know that this current through 20 ohm, we have already calculated here, is 5.75. So this current is 5.75, which will not flow through the CT. Total current here is 6.38. This 6.38. But this 5.75 is not going to flow through the CT2. What is the current through CT2 is 0.62. And this current is same 3. Sorry, what was that? 3.19. Now see, what is current through CT2 is 0.62 ampere. Therefore, I2 is 0.62 divided by 4. That comes to 0.62 divided by 4. That comes 0.155 ampere. What is current through CT1 is 3.19, and therefore what is the primary current is 3.19 divided by 2, that is 1.595. Now you can see the current from CT2 and CT1 are not going to be the same because there is an internal fault. So if we find the percentage bias, it is I1 minus I2 upon I1 plus I2 by 2. So that comes 1.595 minus I2 is 0.155 divided by 1.595 minus what is this coming? 1.595 minus 0.155. What is the percentage bias coming for this case? Yes. 1.44 differential current divided by 0.875. So this comes as 1.44 divided by 0.875. That is 1.64. Now suppose if we have set percentage bias, set value in the relay is 0.2, let's say. Suppose in this relay, then obviously this 1.64 is greater than set value, so relay will trip because it is an internal fault, winding fault. So we need to take care of this, and it can be it can create even physical damage, structural damage to the winding. So for this case, the relay will trip. Okay, this is fault. What we did here, we have closed switch S2 fault on internal fault. Secondary side. Likewise, if we calculate it for internal fault on primary side, in this diagram, if you see, if we close with S1, this 25 ohm, so the diagram will be like this. (185 ohm). This is, if we close with S1, you can see here, this is 25 ohm, CT1 2 by 1, CT2 4 by 1, 230 volt, 115 volt. So what is current here? 230 volt by 25. That is a current to this fault path. 230 by 25. 9.2 ampere. And this current, load current, is 115 by 185. Is 0.62. So here it is 0.3. 1, you can see. So 9.2 plus 0.31, that is the total current on primary side, you can see. It is 9.51 ampere here. This is flowing through CT1. Current through CT2 is 0.62 because fault is on primary side. So you can see I2 is 0.62 divided by 4, which will be the same, 0.155. I1 is 9.2 plus 0.31, that is 9.51 divided by 2, CT ratio. That is 9.51 divided by 2 is 4.595. And if you find the percentage bias, you can see I1 minus I2. So I1 is 4.959 minus I2 is 0.155 divided by 2. And this will come as 1.872. And obviously it is more than set value. So relay will. So in this experiment, what we have to understand is that when switch S3 under normal condition, current through both the CT will be the same. Although they are identical, but still there will be some spill current flowing through the relay coil. Okay, but that current will be small enough that will not create any problem to relay operation. Next thing we are going to understand that when we create the external fault, although the current is higher, but still if the bias setting is not satisfied, relay is not going to trip. And in case of internal fault either on primary or secondary side, the relay will operate instantaneously because the percentage bias is seen by the relay. It will be more than the set value. Okay. So this is the operation we have to look after in the next laboratory. So I will demonstrate the experiment on parallel feeder protection and transformer differential protection using bias differential relay in the next laboratory. Okay. So anyone having any doubt? I'll also upload the guideline for experiment, these two experiments, how to write it on the canvas. Okay. Okay. So just a minute. Every one of you, please enter your enrollment number and stay in the session. Okay. Do not leave the session. Everyone. We want to discuss some important points. So please first enter your enrollment number and then let us discuss. Do not leave the session. Stay. Okay. Just so here I am ending the session. We will discuss some important points. Okay. So stay in the lab.